We'll continue the discussion we started last week on near inertial oscillations, and he's going to talk about mapping the dynamical components of surface currents with Odysea and further perspectives for inferring ocean subsurface properties from wind plus current. So thanks for presenting, Clément. I'll let you take it away.
Thank you, Sarah, for hosting this event. So yeah, I'm Clément Ubelmann, working in Datlas, Grenoble, France. And so today's topic is going to be closely related to last week about near inertial currents in relation to Odysea. And if you've seen Jimbo's presentation last week, it was a very nice overview of the challenge and overall the opportunities of near inertial oscillations in Odysea. So with a very convincing result. So hopefully today I won't disappoint, but I will try to bring some complementary elements or materials in that same direction. In particular, an introduction with some quantification of how much of the total current is actually known, resolved today or modeled today. And also in second part, I will go over this 2D mapping algorithm that was identified as potentially interesting for mapping both near inertial current and sub-inertial current or even a geostrophy. So in a single algorithm to handle the different components. So then I will, in the end, in the last part, propose some very preliminary thoughts beyond the surface current, and in particular, if what we could infer from observation of both wind and current. This is more to maybe open the gate to some future studies during the preparation of the mission. First, as an introduction, so last week you saw a lot of moorings data. So for a chance this time, I will show a lot of drifter data, which are also a great data set to get a flavor of what a total surface current is. It's like a ground truth, so very local and sparse, but a ground truth of the total surface current that contains all the components. So that's interesting to look at some time series of that and also to compare with what is resolved today. So if we collocate the data here from the geostrophic field from Aviso at the drifter location, here's what we get in the animation. So the geostrophic current, sorry, I'm just moving that window. So the geostrophic current seems to explain a fair portion of the low frequency component. So we can do actually from all the drifter more quantitative validation to look at how much is actually resolved. So I propose this metric here. So from the time series here in black of the drifter observation and in green the estimation, we can compute the PSD, the power spectral densities of both signal. And more interestingly, the PSD also of the difference of the signal, so the estimation minus the observation. So if the estimation were perfect, the green curve would be 0. But it's not, of course, and we can characterize actually the ratio of how much is well resolved with respect to the total current. And here it's represented under the variance preserving form, which is not always convenient, but I thought that here for this case, that offers a view of the variance. We can clearly see how much of the variance as a function of scale is explained by the resolved geostrophy from altimetry with respect to the total current from the drifters. And at the bottom here, this is the percentage of the ratio, this what we call a score. So we'll use that matrix all along the few slides of introduction. And here run in a North Atlantic box at the top for clockwise, in the clockwise direction and counterclockwise direction. Subtropical at the bottom. So here you can clearly see the big inertial peak that is shifted to a lower frequency as in the subtropical. Of course, this peak and the tidal peaks as well are not resolved as expected. And we can see here that geostrophy so explains a fair portion of the current at low frequency. But finally, what's interesting is there is 50% missing. So even even at low frequency. The geostrophy, and where the geostrophy dominates around like 30, 40 days, there is still 50% of this low frequency current that is not explained by geostrophy. Something to keep in mind. There are some, some attempt to model beyond geostrophy the Ekman current from the winds products. So how this is the example of the Siemens product that contains the simulates the Ekman component. So this is actually empirically given by the drifters. From the drifter data, there is an empirical relation that that makes a transfer function between wind and current. With this current here in blue that is always like at a certain angle and with a certain ratio of amplitude with respect to the wind stress vector. So that should explain a part, at least, of the Ekman current. And here is what we have when we again collocate that on this same little drifter. So that adds a little bit of signal here compared with the green curve that was the one I showed just earlier, the geostrophy only. So it's a small contribution, but not negligible. That's going to be confirmed next slide in the quantitative validation. It's also interesting to see that the first kick of some NIOS events seems to be kind of well resolved. So actually there are some good reasons for that, and we'll see that in the last part. But of course there is not following oscillations because by construction, the Ekman estimation is locked with the wind. Here are the quantitative analysis. So in the low frequency part where we had about 50% explained by geostrophy, we had about 10% improvement in RMS. So that's interesting. That also means that there is 40% missing. So even with Ekman estimation, and it's probably similar, I guess, in Oscar. So there would be 40% missing, even at scales that have no sampling issue in the observation systems, right? And also note that Ekman is small, but it's a very worthy contribution because there are some divergent properties. And just for reminder, of course, the geostrophic velocity has no convergence and divergence. And actually, that's very essential for particle transport. I remember Eric Van Seville made really nice illustration of this point. So, but 40% missing. There are some ongoing efforts to also tackle the near inertial band, even with the observation we have today and the wind we have today. Although it's not yet in standard observation product, it's solved different ways with Odysseans. They do resolve them. But that's also very well represented with a 1D vertical model like this one. Even a slab makes a very good job in simulating, representing the NIOs quite well in phase. And also there is the transfer function approach, which can do also the job of a 1D vertical model. And that's something we investigated recently. So I will not right now focus on the method. I will talk about this in the third part. But for now, I'll just give the result of what we get by actually fitting a transfer function empirically from the drifter database. And here is a comparison with an independent drifter, so that was not used to compute the transfer function. So first thing is, well, some NIOs are well represented, and I think that's totally in line with the Jimbo's result from the slab models and also from the MIT GCM model. But clearly there is missing current, and for two reasons. First, winds are imperfect. The wind stress has errors and also has missing content. In particular, does not contain all the short scales. And also the ocean response operator is assumed large scale and climatological here, ignoring local stratification profile, relative vorticities, terrain advection, and so on, because we don't know the interior of ocean. But what's interesting is that with Odyssey, we may go beyond actually on these two aspects, which I think is interesting. So this is the end of the conclusion. So this is the quantitative here diagnostics that confirms that a large part of the NIOs is still missing. So if you look at the red area versus the total gray area, there is a long way to go. And that brings to the question that if we have direct observation from Odyssey, there will be some lot of unknown at near inertial frequency, and the challenge is how to handle that. And here I remind Jimbo's conclusion that actually brings to this to the presentation of this study that was conducted in 2019, so 3 years ago, in the context of the scheme concept. That was a project we had in the European side. Actually, it's good to note that the scheme concept had time revisits much longer than Odyssey, which actually will make here the problem much easier than it was with scheme. But in that time, we also tried to tackle the problem, even though the time revisits were even longer. So very few quickly, an overview of what was this scheme mission. So it's also wide swath 2D for designed for wide swath 2D surface current, total surface current observations. And of course, so the challenge was to reconstruct the total current with typically 2 to 4 day time revisits. So we conducted some OSSEs based on a numerical model to assess and to test and to design different methods of mapping to reconstruct the current from synthetic data here following the scheme concept. So we start from numerical model. Here the NEMO NATL run as a ground truth that has all variable, and in particular surface variable in SSH and in surface current. From these variables, we could generate some synthetic observations. So of both altimetry and Doppler surface current. So here, by the way, you see what was 2 days worth of scheme, and actually 2 days worth of Odyssey would be already complete and even 2 to 4 times revisited. And then we tried a different algorithm for reconstruction, and in particular reconstruction of the surface current, to be compared with the ground truth, which is here the general principle of OSSEs. Okay, so first, well, we applied the very standard mapping of Aviso to reconstruct the SSH field. That we compared to the SSH, but also compared to geostrophic velocity, and ended up here with what we call a score, reconstruction score of around 110 kilometers, meaning that all spatial scale between infinite and 110 kilometers are well resolved. So by the way, it's unfortunate that here the scores are represented as a function of the spatial dimension. We could also have done the time one and to be consistent with the introduction of drifters, and with the drifter we cannot do the spatial one, but at least we'll have seen the two views, space and time. So here is in space. This is really consistent with the real data observing experiment that we can conduct. So that's, I think, we think pretty realistic OSSE here. So then what we do if we do also a basic mapping of the total current, so independently from altimetry. So this is a bivariate mapping of UV from the radial currents in both directions with a basic OI, so with a covariance function that is basically a low pass. And we get the black curve. So interestingly, we do a little better, slightly better job for short scales. And that's actually explained because the revisits were a bit higher than the one of altimetry. So here again, with Odyssey, the revisit would be even much better, and we might expect more than 15%. And at large scales, quite a poor job because of some issue I'm going to explain soon in the next slides, and no control at large scales. And why? So we can look at the geostrophic estimation. So since we mapped the geostrophic field from the altimetry, so we have the ultimate geostrophic component, we map the total field here from scheme. So we can look at the difference, which should be our geostrophic estimation. And if we compare with the true geostrophic currents, that's pretty disappointing. And here comes the challenge and the issues. Especially if we look at 2 days, 2 days apart, here and here. Of course, the geostrophic fields moves a lot because of inertial motions, but our estimation, which is by construction only low frequencies, is very bad, totally aliased, and which is shown here. So that was already very well illustrated last week. So this is the aliasing of the NIO aliasing issue that gives a very poor score. But actually, we can take advantage of NIOs on the fact that it's a narrow band signal, meaning that even if the scale itself is short, it's the oscillations are predictable and have some coherency over a few oscillations. So we can exploit that by actually defining some appropriate covariance, and actually the plan is to do that for the different, hopefully all the different surface current components, and also internal tides, by the way, but which I will not detail today. How we constructed this covariance function. So the NIOs can be locally expressed under this form because it's a rotating field in the clockwise direction. And also, we know, when we say we know, this is yet also to be better confirmed with actual observation, but that it's mostly on large patterns. So that's why we could construct covariance functions with quite large scales and oscillating content. So this is with this sort of kernel that we conducted the mapping. So for this particular here NIO component, and then after implementing that, we can so run what we call improved mapping with the different components. Each of one has specific covariances. Sorry, and see what we get. So first, for geostrophy, it's interesting here to know that with this improved mapping, we can also improve geostrophy. So here you can see the red curve, so which is this simultaneous mapping that is over all the curves. So it takes the better of each curve, actually, the better of altimetry at medium to large scales, and the better of here scheme at short scales. So that's good to see that. And then for geostrophy, now we can have a really decent job. So this is here the reconstruction here compared to the ground truth on the right. Of course, we do not resolve all the very short spatial scales, but the large patterns are quite well resolved if we compare between 24 hours apart. Of course, the field moves a lot and we cannot capture the motions. This can be seen here as a function of time. So now, with only this handful of observation, you can see here, typically sometimes we have even 3-4 days gap, we can still reconstruct a part of the NIO. So that's one interesting thing. And the other is that also the altimetry helps, actually, because it's part of the system and it acts in synergy to better separate all the components. Well, here that's far from 100%, but this was with typically 2 to 4 day revisits, which is much longer than we could have with Odysea. If it's between 1 or even 0.5 days revisit, we could really expect this is to be confirmed, but almost all reconstruction of NIO, I think, by really here accounting the narrowband properties of NIO, both in time and also the low wave number in space. And of course, with this joint use of altimetry that helps. This can also be actually summarized in one message, is that for narrowband signal in general, so that here for NIOs, but also for internal tides with SWOT, for instance, what matters for mapping or for resolving or the inversion problem in general is not the scale itself. Here, for instance, which in 1/f, of f being Coriolis, but the coherency, so 1/delta-f, so the width, 1/the width of the peak with respect to the observation sampling. And there are also other recent studies that around about internal tides for SWOT that totally go in that direction. Then, well, that's my little like animation of I think one of the biggest NIO event that I could find in the North Atlantic by looking at the whole series for almost like half an hour, looking at all the drifters for like a 6 or 7 years period. I found this one really nice. Well, look, that's actually interesting to see. That's a combination of several factors. We had a very strong wind event, and it's going to be now here. This is the wind stress in green, and the wind stress so increased a lot and happened to turn clockwise the way the wind pattern goes through, makes a wind locally turning clockwise for 4 to 6 hours at near inertial frequency. So it's probably very fortunate that the wind turned right at the frequency that that inputs all the energy to NIOs. And on top of that, this was a summer and August, and in summer the mixed layer depth is very shallow, so there is very few inertia, so it's very easy to put the first layers of the ocean in motion. So we have almost like 0.7 or 8 amplitude NIO signal. Well, that's also nice to look at what was resolved that day from the different estimations. Geostrophy, well, you can see geostrophy, some oscillation. That's actually the Lagrangian effect of the particle moving in the geostrophic field, which is almost steady at this time scale. But since it's moving in the field, we have this sort of small oscillation. We also see this first kick of NIO resolved by the Ekman only solution in blue. And we have the oscillation that is decently resolved, but with a lot of missing signal. Here in red with the total, with the Ekman, the unsteady Ekman, so Ekman plus NIO estimation. So now I'm gonna give few perspectives beyond surface current. So first, mapping NIOs would be great for sure, and probably with many direct applications. Short-term Lagrangian advection, for instance, or some rescue, or so maybe impact on longer-term Lagrangian advection, I don't know. But also beyond this, observing both winds and NIO currents is finally like observing an input and output of an ocean response operator, which is well described with a 1D a simple model that involves the kappa profile, which is the the viscosity, the vertical viscosity. And at these scales, I think we should think this scheme is right. I mean, it's a one-way interaction from wind to ocean response, because it's very the direct response of wind. And actually, if we consider that this problem can be solved with a transfer function, we can try, I mean, that opens a lot of perspective for Odyssey, but even now with the data set we have today, we can try to get a flavor of what we could get and what this ocean response operator would look like. And we propose here a preliminary study test with the drifters and to evaluate the potentials, and then of course to be used with Odyssey in many more aspects. So we tried that transfer function in the time domain. So in the time domain, then it's a convolution. If we consider only the Ekman problem, the steady Ekman problem, so actually this transfer function is a single multiplication in the complex space. So a single point. So that's why here the blue arrow is always has always the same ratio and angle with respect to the green vector, which is the current. But then when you consider this unsteady problem with convolution function, you can generate a convolution function that reproduces the surface current behavior. So of course, here all the question is how to get this time convolution function. And here we solve the data-driven inverse problem from the drifters. So we have u of the velocity from the drifter. We remove all what we know is not part of this physics. Here, for instance, the geostrophy. And we assume this is explained with this convolution with the wind plus epsilon, which is the rest, okay? Then we solve this inverse problem. It's a linear, actually it's a linear problem, so quite easy to solve with conjugate gradients. And we get a convolution function. So I thought it was really interesting to look at what at this convolution function, at this ocean response operator. First, well, we know that the present current shouldn't be affected by the future wind, right? But it's really nice here to verify that. So we resolve the convolution function between -7 and +7 days. And what we found, if we have noise in the positive time, so that means that the future wind does not have a statistical impact, an impact on the present current. And then in the past, we have this dominance. Here we have the real and imaginary part, which here is represented in the complex form real as a function of imaginary part, which is a convolution function that actually triggers all the energy from the wind that is at a near inertial frequency into rotating near inertial oscillations. And what I found interesting, and with probably some perspectives when we'll have much more surface current data and even surface current wind data, is that even here from the drifter database, we can already characterize many things from this operator transfer function. For instance, we can see that in the summer, the amplitude is much larger because, as we already saw in the example of the drifter in August in North Atlantic, the mixed layer depth is shallow. So the transfer between the wind and the current is very high. So even if you have a little bit of wind, it can be transferred into very energetic oscillation, rather than in winter, the mixed layer depth is very inert. And inertial oscillations are harder to trigger. So it's interesting. We certainly see some patterns related to mixed layer depth. So we can maybe open some perspectives, say, well, with Odysea, when we have almost constant observation of near inertial oscillation everywhere and wind, we could solve this G function at high resolution in time and space and tackle all the dependencies with the variation of the kappa profile for a numerical model, or maybe with maybe many applications. But this is well, this is perspective. I don't know if that's a dream or not. So next steps would be to conduct the pure statistical 2D plus time mapping study that was run with Kim here with the new LLC run and Odysea design with sampling and noise. So if would be worth to put the effort if the NIO challenge is still considered as a potential concern. Also finalize the NIO characterization, in particular the EKE spectrum from the drifters, to sort of confirm that most of the energy is at large scales, and that would give some confidence to the OSSC we can conduct in the context of the Odysea mission development. And also, well, to further investigate this unsteady Ekman transfer function. Looks like it was very interesting, and a very interesting paper by Lilian Elipot for a very in-depth theoretical background. Some other important consideration, well, this is a detail, but I think it could be important, is that you should remind that Ekman is weak, okay? The low frequency part is weak, but has a huge impact at low frequency, in particular for garbage convergence in the ocean. And in the context of Odysea, we may ensure that all the correction processing, typically based on signal RMS reduction, does not deteriorate Ekman current observation. For instance, using a slab model for an NIO correction, we know that the slab model also do Ekman, but does an Ekman at 90 degrees of the wind, okay? Because just one layer is the integral. So that could introduce some spurious Ekman if we apply the correction on the surface current, for instance, unless we do appropriate filter to get the NIO part on. And also, yeah, I know that I think the equatorial current should be really specifically addressed and in the context of Odysea mission. So I'm going to stop here. I don't know how long I took, 30 minutes.
That was perfect. Thank you, Clément. Big round of applause. And questions for Clément? So maybe to get things started, I'll just ask, in your example of the biggest event, was that a hurricane?
No, I think it's a storm, yeah, a mid-latitude storm. Well, it is 46 degrees. It's probably a mid-latitude storm, but a summer one. Which typically are smaller, not as intense, but in terms of NIO, because of this shallow mixed layer that can trigger NIOs. Yeah, that means I haven't looked at more like extratropical drifters to pick my event. So maybe that's something we should also look at, more equatorial drifters to see if we see interesting stuff. Yeah.
Tom Farrar has his hand up.
Clément, really nice presentation. I think that's really interesting, the results you're getting with the transfer function and using that to infer mixed layer depth. I was wondering if you have a sense of what kind of time, space, resolution you could get out of such an estimate.
Yeah, because here we had to define like a 5 by 10 degree grid and assume only one harmonic for seasonality, because drifters, I mean, we don't have much drifters, so we have to, because otherwise this noise level is very high. Okay, and then I guess it really depends on how local actually are the effect. Like, also, if there is some correlation with the eddies, maybe we can, to reduce the number of the degrees of freedom, we could also use the SSH, and maybe there is some correlation, use the altimetry and so on. But then, yeah, I would guess this is clearly related. There are some very local effects, like when you have a front, you have strain, and then the inertial signal can be totally out of phase. And I think in this kind of condition, like even the resolution of Odysea wouldn't be able to kind of capture the local in space and time G transfer function. But otherwise, maybe there is some big patterns that we could control over time that would be related to big eddies, and yeah.
Well, that your answer brought to mind another question, which is what's the best real-time wind product? Or, I mean, the quality of that estimate also depends on the quality of your wind, and especially the time resolution, which, you know, as you go to like 6-hour wind, it would degrade the transfer function a lot.
Yeah. So that was hourly wind, and that's very important to consider. So this was the ERA 5 hourly winds, but that's the standard product, the one in Copernicus, available in Copernicus and everywhere, I guess. There are some ongoing effort in the context of that same project in which we investigated this transfer function. There are some ongoing effort to assimilate and make like what they call ERA 5 star product with improved stress from scatterometers. They combine the ensemble of scatterometers, and this is to be tested. We're going to test that soon, but Yeah, that would help actually to know between the two reasons, which is missing wind and inaccurate wind and inaccurate transfer function, at least which one is the most dominant. It's hard to know. We know that both are important, of course, but yeah.
Maybe in that vein, I'll ask, you were emphasizing at the end that the slab model has the problem of putting the Ekman transport at 90 degrees to the wind. But you also talked about the unsteady Ekman model, and I'm wondering how much of the problems stem from the unsteady part and how much just from the vertical structure of the Ekman layer that would be included if you weren't using a slab model.
Well, I think this, if it's the full, not sure that, if it's the full 1D model,
Mm-hmm.
then in theory, we should be able to, to model all the Ekman spiral
Mm-hmm. Mm-hmm.
and avoid maybe this kind of effects.
Avoid all the simplifications.
Yeah.
Yeah.
But yeah, with one layer, we don't have the choice. So
Mm-hmm.
but if the near inertial oscillation itself are perfect with a slab, then why not? But we just be careful not to include its a mean non-zero component right at 90 degrees of the wind at
Mm-hmm.
all. Maybe.
There's a question in the chat from Ali Payanda. Do you want to go ahead and ask that, Ali?
I haven't seen the chat yet.
Or I can read it. How can you differentiate between tidally induced eddies and inertial oscillations, especially in mid-latitudes, where the inertial period is very close to 24-hour tidal oscillations?
So what do you mean by tidally induced eddies? Either, do you mean inertial internal tides, or do you mean internal tides or eddies?
Well, the question's relevant for internal tides.
Yes.
For
Yeah.
sure.
Yes.
Tidally induced oscillations, I
well,
suppose.
Well, it depends in which context. Well, yes. Well, for coherent internal tides, that's coherent. So we hope that with simple harmonic analysis, we can separate them and it's not an issue. Then for uncoherent internal tides, I think it's the same. Well, it's pretty close problem to NIOs because we have a certain period of coherence that is probably longer than NIOs. I think it's typically 15 days. It's related to the large eddy pattern because it's mostly the first baroclinic mode that drives this inertial dominate the signal of internal tide. So same. I mean, with a statistical mapping that the one presented that didn't include tides. That's right. We could imagine to simultaneously have actually I illustrated that, and we actually are doing some effort right now with a PhD student from Le Guillou about mapping uncoherent internal tides, and that could clearly be done in the same global mapping of all components. We just add a component and solve that. Of course, then there is some region where is the result? I think it's in introduction. The peaks are clearly distinct, like for instance at lower latitudes, so that would going to be easier. And then at high latitude, when you get close to North Pole, the two peaks are very close. So it's probably a bit more challenging, but anyway, I think especially in the north, it's not as big as inertial oscillation, and probably if we remove the coherent part and the barotropic component, which is coherent, maybe we can reduce the peak a little bit. But yeah, good question. Yeah.
Yeah, I was going to ask along the same vein, and I'm glad you're on this figure. What are the prospects for dealing with the tide, and should that be dealt with separately, or?
You mean with in this like
in that 5 to 25 where you've got a very distinct tidal peak?
Yeah. Well, so as I said,
it's clearly a lot of the variability. So
yeah, for the coherent part, it's clearly like to get it separately from harmonic analysis. I think we should look at the we should we should have included the FES model or another Taiwan model operational outputs, because maybe we would have seen how much of this peak would have been explained. Also with the internal tide solutions like the one from Edzeron. And then beyond that, maybe that's, well, we're working on that with SWOT, but also in the context of Odysea, I think it's really there too. And yeah, that reminds me, there is a very interesting paper that came recently by Gary Egbert that showed that actually it's the same as NIO. They exploit the coherency and time of the internal tides, and also the fact that the spatial patterns and actually finally the whole signal in time and span can be reduced with very low dimension space, like a bit like we did on NIO. And they were able to do a very good job at reconstructing uncoherent internal tides from SWOT-like data. So I think it's probably the same approach. So.
Can that all be woven into the same analysis system, do you think?
Oh, sorry, I didn't hear.
Do you think that could all be done as part of the same analysis system, the same retrieve, as an expansion of the method you're using?
Yes,
or?
yes, I think so. Yeah, because we're defining actually covariance with reduced space. So we could include that reduced space like another column. Mm-hmm. And then we run the inversion system on the global stuff. Yeah.
Interesting. Momi Hell has his hand up.
Yeah, hi. I think you can hear me. It's related to this formula and to Tom's question about error 5 and error star. So when you do in your inverse problem, I did not exactly get how you do it, but you should get an uncertainty on your parameters, and you probably also have to assume an uncertainty for the winds. And so when you talked about we do not really know the winds correctly or correctly enough, but what do you do there, and how can you deal with propagating the uncertainty to your estimate?
Yeah, you're right. I think what we do actually, we say, okay, that's in epsilon, like that's everything we can explain from the wind we have. That of course contains many errors, and everything is in epsilon. So I mean, if the wind was really crap, we would have like anything here, would have like something tending to 0. That this really nice pattern here shows that well, at large scale actually RA5 is pretty good job, it's doing pretty good job. I mean, you can see here the NIO event is really well picked and reproduced. So yeah, RA5 is pretty good at large scales. Probably a lot of problem at small scales and short time scales. And we consider that being in the epsilon. And that's maybe also where Odyssey can help to get better wind product, I guess.
So, but then you can phrase the question what the resolution is you can achieve, right? So you have to assume some spatial average or whatever, and with that you can like reduce the error by averaging, but at the same time you lose resolution.
Yes.
And there might be there's some optimal point.
Yes. Well, I think since RA5 is a model assimilated, it looks like there is not much unresolved scales. It's just that the field is smooth. I mean, it's a 1/4 degree grid, but I think even if you do a spectrum, it drops below like 200 or 150 kilometers. So that's all the missing content. I think that's mostly missing than errors, but well, there's certainly also errors, of course. Yeah.
Okay, thanks.
Yeah, it would be good to investigate a little more, I think, in the context of this preparation of the mission and really how much of the wind we actually have today. Yeah.
Very interesting. Yeah. Good. Thanks.
I'll let Tom go ahead.
Clément, have you calculated what fraction of the variance, is in your residual that you're not capturing through your fit?
That's That's here, basically. So that's the red one. That's the one we got with the transfer function. Okay. So red, that includes the blue plus the green. And the gray is the whole current. So we see that here with all the assumptions we had to make because imperfect wind and very few drifters. So large scale transfer function and only one seasonal harmonic, we capture about even a bit less than 50% of the NIOs. And also, which also I think is really interesting, I want to come back on this point, is that at large scale, so at long temporal scales, where I think observation system doesn't have any sampling issues, there is still about like we're about 50% missing. So unexplained surface current, even slowly evolving, that is not captured today. So,
Clément, I think the information is maybe there in that plot, but it can be kind of, you know, I don't know if misleading is the right word, but these variance preserving depictions, you know, there's like a lot of variance at low frequencies that's maybe just not represented because you have a short record.
It seems to drop.
Yeah, but it's multiplying it by 0, basically. I don't know. I think it would just be, I think, worth calculating the number, like the total fraction of the variance
that is
not captured in the inertial band.
Very good suggestion. Yeah, because we can do that with the drifters. Yeah. Okay. The thing is, I couldn't extend to really beyond because then you lose a lot of drifters that are not continuous for more than a month. But then we know. I mean, we can know with the fraction with respect to the total current. And yes, it's very good.
Right. So that was one point I was sort of getting at, is there's a ton of variance at timescales longer than a month. You know, so that if you take a short record and do this sort of depiction, there's just a bunch of variance that you're not looking at.
Yeah, or maybe the variance itself is not that big, but can have huge impacts for science and oceanography.
I mean, mesoscale eddies, I think it's big. You know,
that's the 1 meter per second current, and I see that low frequency there is no 1 meter per second current, very slowly varying in other direction. But that could be, I think, extremely important to characterize this. And it's not because even if the variance is small, that it's not important. Could be very important. So, yeah.
Okay. Well, I'd like to talk to you more about it.
Yeah. Definitely. Yeah, that would be great. Yeah.
Well, I'm also curious if there's any geographic variation in how much apparent skill you have. So, for example, are the wind products worse in the southern hemisphere than they are in the northern hemisphere? And would you see that in trying to do this analysis globally?
Yeah. We've only conducted that in the North Atlantic. Yeah. It would be very interesting. Yeah.
And of course, I'm really curious what's going to come out when you try and apply this with the Odyssey swath and revisit times.
Yes, because doing this kind of stuff on a numerical model with Odyssey data, maybe characterize until how much we can reconstruct this transfer.
Do you have any speculation on that?
Sorry?
Are you able to speculate now about just in terms of the expanded coverage, what it might mean? Do you think you'd be able to get double the skill or quadruple the skill?
Probably. You mean for? Do you mean for the G transfer function or for the how much we reconstruct here?
For how much you reconstruct, for example.
Well, the study conducted with Kim, so that showed like about 50%, and the NIO was small, which is actually not in favor for the NIO reconstruction because the NIO were small in this model. They are much bigger in more realistic new LLC run. And really, it was like a typically 3-4 day time revisit. And now, if we consider the 1 day revisit or half a day, I think we solve everything for NIOs. almost everything.
So,
Probably
yeah,
over 90, I don't know. This
really different picture then.
yeah.
Well, we'll all stay tuned. Any other questions today? If not, we'll wrap up. Thank you very much, Clément. This was really wonderful.
Yeah.
Big round of applause again. And thanks everybody for participating.
Thank you.